All right. Hi, everybody. This is the LA Joy. On the midterm survey, a lot of you guys indicated you'd like to see more answer keys and results, and a lot of you like to see examples worked out. So since we're not going to be meeting in person for the rest of the year, I thought I would try going over, some of the solutions to the worksheet from the week before spring break. If there's any changes you want me to make about the way that I would do something like this, let me know. If these types of videos are helpful for you guys, where I go through and work out and explain the answers, definitely let me know. I can keep making them. This is just kind of the test option, right? So this is worksheet 8. So this is from the week before spring break. We went through kind of a math case study of Gabriel's horn, which is this shape right here. We use the function f of x is equal to x to the negative 2/3, where x is greater than or equal to 1, rotated around the x-axis, so it looks like this, right? To infinity, right? Starting at x equals 1, somewhere in there. So when this gets rotated around, we get a series of circles, like that, and that's what we're going to be looking at that makes our function, right? So the first one wants us to write the integral, so an improper integral for volume, and show that it's convergent without evaluating it, right? So when we do this washer method, right, we think back to Calc 1, we say, okay, so we know how to do this, right? We're looking at an interval from here, 1, because that's where we start, to infinity of area x dx, right? So the area of each one of these little shapes, right, is a line, and we rotate it around and we get a circle. So we say the area of a circle is pi r squared, where the radius of each circle, right, we start at the x-axis and we go up until we hit the function f of x, right? So the radius is x to the negative 2/3. That's what our function is. So then our area is pi x to the negative 2/3 squared, right, which is pi x to the negative 4/3. So that's what we put in our integral up here. We're going 1 to infinity of pi x to the negative 4/3 dx, right? I'm going to rewrite this just a little bit because I like to have the constants on the outside. It doesn't change the answer at all. It's just a habit that I'm in. I think it's worthwhile to do, right? Helps me keep track of my constants a little bit better. So that's the first part, right? We've written down the integral, and now we need to show that it's convergent without evaluating it, right? And it says we should use the p-test. So quick review of the p-test, right? It's a series convergence test, looking at series where we've got 1 over x to some power. We start at 1, we go to infinity. So if this power, which I'm going to call p, is greater than 1, this is a convergent series. And if this is less than or equal to 1, this is a divergent series, right? So right here, we've got basically this integral, right, which I'm going to write this way, x to the 4/3 dx, right? So we've got 1 over x to a power. Here, our power is 4/3, which is greater than 1, yeah? So the integral converges by the p-test, right? If this was a test, I'd want to write out the integral converges by the p-test, right? But it's a worksheet. It's not turning it in for credit. This is for you guys to see, right? So the second part of the worksheet wants us to evaluate our integral and find the volume, right? So we're evaluating the one we just wrote, right? X to the negative 4/3 dx. This is an improper integral, so I need to write it as a limit. The pi doesn't affect the limit either, so I'm going to go ahead and also pull that out to the front. Now we're going 1 to b, x to the negative 4/3 dx. So that is just power, right? This is power rule, yeah? So pi times the limit of b goes to infinity, right? So we're going to do negative 4/3 plus 1. So it's negative 1/3, flip and multiply for negative 3, x to the negative 1/3 from 1 to b, right? So I've got a constant here in the negative 3. I'm going to pull it out with the pi. So negative 3 pi, the limit as b goes to infinity, right? So my top value is b. So 1 over b to the 1/3, right, minus negative 3 pi, limit as b goes to infinity, 1 over my bottom value, 1 to the 1/3, right? So this up here, we've got b goes to infinity, 1 over b to a power, right? So the bottom of this is going to go to infinity, the top is going to stay at 1, so the bottom's going to get big really, really quick. So this is going to go to 0, right? And over here, 1 to the 1/3 is just 1, 1 over 1 is 1, limit as b goes to infinity of 1 is still 1, right? So we've got 1 times negative 3 pi, right? So this is negative 3 pi, right? So we've got 0 minus negative 3 pi, so that's plus 3 pi, is equal to 3 pi. So this is the area, this is the volume for our Gabriel's horn, right? So moving on to the next one, we're going to surface area, right? They've got a good explanation up here for how this works. I'm not going to go through it right now, right? If you are going to take more calculus classes, it's worth doing this at some point on your own, just to read through and understand how they're going to set this up, right? Because this is something that if you're taking more calculus classes after Calc 2, you're going to see it, right? So it's a good intro to that. The Pythagorean theorem, right, is they're just using this triangle here, the dl, dx, and dy, and some clever algebra, right? In this step right here, the one you have to remember is that f prime of x, right, is equal to dy dx, right? That's what a derivative is, right? There's just two different ways to write it, so that's how they're making that jump there. So we are going to go ahead and kind of skip through that and just look at how you would set this up, right? So we would set this up, I'm going to use SA instead of A because I already used A, right? From 1 to infinity, right, of f of x root 1 plus f prime of x squared dx, right? So our f of x is our original function, which was x to the negative 2/3. F prime of x then is negative 2/3 x to the negative 5/3, right? We need to do f prime of x squared for our formula, right? So that's negative 2/3 x to the negative 5/3 squared, right? Which is 4/9 x to the negative 10/3, right? So when we plug all this into our formula, right, we're looking at the surface area is equal to 2 pi, the integral from 1 to infinity, f of x is x to the negative 2/3 times the square root of 1 plus f prime of x squared, which is 4/9 x to the negative 10/3 dx, right, which I'm going to write slightly differently as 1 to infinity, 1 plus 4/9 x to the negative 10/3 over x to the 2/3 dx, right? So here's our integral for surface area, right? It's just identifying the pieces of the formula, plugging everything in, right? So the fourth part of this, coming to the end now, actually has a typo right off the bat. I didn't notice it when we were in recitation a couple weeks ago, but I've definitely noticed it since then, right? So the comparison theorem right here has a typo. So part B should say if the integral from a to infinity of g of x is divergent, then the integral from a to infinity of f of x is divergent, right? So if your larger function converges, so does the small one. If the small one diverges, so does the large one, right? So this one is kind of weird. We've got to find another function. We've got to look at all these different things. I've gone ahead and written out, right, the one right here. I tried a few different ones. I think this one's probably the easiest to do. So we're going to look at the function g of x is equal to 1 over x to the 2/3, right? So one of the things we have to show is why the comparison is valid. So I'll write this as valid, right? Question mark, right? So we have to show that f of x, which was our very, very long integral up there, right, our integrand, 1 plus 4/9 x to the negative 10/3 over x to the 2/3, right? Let me make sure I got that correct. and yes, we're good to go, right? Is greater than or equal to g of x, which is just 1 over x to the 2/3, right? So if we multiply both sides of this by x to the 2/3, right, these cancel here, this cancels here, right? So we've got 1 plus 4/9 x to the negative 10/3 greater than or equal to 1, right? Square both sides, just doing some basic algebra, right? 1 plus 4/9 x to the negative 10/3 greater than or equal to 1, right? So we know that this quantity right here has to be positive. X to the negative 10/3 is always going to give a positive number. Times 4/9, another positive number, right? We're taking 1, we're adding something positive to it. So of course it's bigger than 1, right? That's a pretty standard thing for us to say, yeah. So this is good. We're done there, right? We have a valid comparison. F of x is bigger than g of x. The part of this I'm going to do next is I'm going to look at whether the integral here from 1 to infinity of g of x is divergent, right? So to do this, I'm going to use the p-test because that's what we used earlier on, right? So this is x to the 2/3 dx, right? So here I've got 1 over x to the 2/3. So x to the 2/3 has got a p equal to 2/3, right? And that is less than or equal to 1, yeah? So this integral diverges by the p-test, right? So we've got two parts of this now, yeah? We've got why our compared function is convergent or divergent, why the comparison is valid, right? So the last part of it that we need, right, is how it's being used, right? Oh, we've also got what function we're comparing to, right? That's the g of x right here. That's a terrible check mark. That's the g of x right there. So we're going to use part B, right? So we're going to say that the integral 1 to infinity of f of x dx is divergent by part B, since the integral from 1 to infinity of gx dx is divergent, right? As our answer to this, right? So g of x is smaller from right here. G of x diverges over here, right? So by part B, f of x, the integral from 1 to infinity of f of x must also be divergent, right? So we get to the end of this, right? And we got to tie a few other parts of this worksheet together. This is why people talk about Gabriel's horn, right? If you want a good explanation of it, there's videos you can look up on YouTube about this, because this is kind of a famous paradox in calculus, right? So I'll kind of point you in the right direction here by saying that Gabriel's horn, right? And these are things we talked about earlier, right? Gabriel's horn has a finite volume, right? We know what this is. This is 3 pi. We calculated the volume, right? But it has a divergent, so infinite, right, surface area. So from the second fact about Gabriel's horn, right, it continues to infinity. You can't calculate the surface area. It's constantly growing. So how are both of these true? How do you have a shape that has a finite calculable volume that we can point at? We can do a little bit of calculus and we can say this has a volume of 3 pi. If you filled it up with stuff, you would fill it up with 3 pi's worth of stuff, right? How does a shape that goes on forever have a volume, right? How does a shape that goes on forever have a volume that I can say what it is? And that is what's up with Gabriel's horn, right? You get these two somewhat contradictory looking pieces of information. So I'll just kind of leave the explanation there. You can look up more videos about this if you want to see someone work through a more thorough version of Gabriel's horn. If you've got questions, you can talk to each other. You can ask me. By the time I send this to you guys, I'll have sent out like some kind of announcement about where and when you can get a hold of me for the next couple months through the end of the semester. So I hope everyone stays healthy and has a good time with all of our online classes. So I will see you in the next one of these videos, or if one of you guys gets a hold of me to ask some questions. So, bye.